So I'm Malachi Phillips. I'm a postdoc out at Sandia National Labs. And today I'm going to be talking about a little bit of a sort of user perspective on using Teko inside Sierra, as well as a feature that I want to put into Trilinos shortly. And I also want to note that this is a collaboration between me and a year-round graduate intern student that we have here at Sandia. So first, I'm going to motivate what sort of problems we're interested in. And these are sort of generic complex multiphysics problems. So for example, I have highlighted here a thermal battery use case, which ends up coupling 15 different PDEs together, including this like coupled Butler-Volmer potential, as well as Stefan-Maxwell diffusion, Darcy's law, and also various continuity solves. So it's a very complex multiphysics system. And I'm going to look at the weak scaling of it from, let's say, 50,000 degrees of freedom to just shy of 500,000. And I'm going to compare two different linear solver approaches. The first one is I'm essentially going to use a domain decomposition scheme, essentially treating the matrix as some sort of black box. And then I'm going to compare that to a sort of physics-aware block preconditioning scheme that is provided through the Teko package in Trilinos. And so here, I'm not looking at the actual time to solution, but just what the linear residual looks like as I'm starting to try and do this solve. And on the left, I have my domain decomposition-based scheme. And on my right, it's my physics-aware-based scheme. So if we look at the plot on the left, and I'm doing a weak scaling, so my 1x resolution is the blue line, 2x orange, 4x green, and then red is 8x. If I do a domain decomposition approach, overlap 1 degree of freedom, and actually do a direct solve, I can reach convergence in about 150 iterations. However, the moment I do any amount of mesh refinement, I can't reach convergence on my problem. There's nothing I can do to recover convergence for a domain decomposition scheme for this particular case. However, I switch over to Teko, and with some carefully crafted parameters, I can reach convergence in 3 iterations. So very happy with that. So as I've shown, the physics-aware block approach provided by Teko works well for multiphysics problems, but it requires a lot of setup cost in terms of complexity from the user in order to sort of specify how to solve the system. So if we limit ourselves to just using the block Gauss-Seidel feature in Teko, the user has to specify 3 things, and they have to get all of these right to get a good preconditioner. The first one is they have to specify how the various physics map to the subblocks. Then they have to evaluate the order of the subblocks. And then finally specify how to actually invert each of the subblocks, which for our users who absolutely hate looking at any sort of linear solver settings is just way too much of an ask. So my goal was to provide this feature in Sierra where a user essentially says, give me a Teko multiphysics solver, and then under the hood, we will generate heuristics to recommend good solver settings to the user so that they don't have to be in the loop when figuring out these individual components. And so this is my sort of cartoon for what we're trying to accomplish here. If you imagine this plot with 2 axes, the y-axis corresponds to like performance, how many calculations you can do. And the x-axis here refers to how easy it is to use this approach for a generic multiphysics problem. Now, if you know a lot about your multiphysics problem, like you're in Navier-Stokes, you can get really good performance by sort of exploiting the structure of the PDE, like especially using operator splitting approaches. And so I say that's kind of the highest performance you can get, but it requires that you know quite a bit about your PDE system. On the other hand, which is where most Sierra users live, they have some sort of generic multiphysics use case that we have absolutely no idea what they're trying to do. So they would just essentially use a black box monolithic solver like DDILU, and it will work, but it will be somewhat slow. Now, they could try and set up a sort of hand-tuned physics-aware monolithic solver like I have shown in the green box using Teko. But that also requires a bit of effort from the user as well in setting those parameters. So what I'm proposing here is let's sort of recover the ease of use of this black box monolithic solver, but also have good performance. And so here's an actual example user application that will use this as a black box-like interface, where you start by sort of making or wrapping your T-Petra matrix into this blocked operator that corresponds to the individual physics. That's outlined in line 5. And then in line 8, you call this generate heuristic permutation, which takes on input that operator. And from there, it tells you how to sort of group the different bits of physics together, at which point you can then reconstruct your operator as on line 10, and then call line 13 to get your settings. And this is all that's required from a user application in order to generate these settings automatically. So the first question I want to answer is, how do we actually pick the right grouping and ordering for block Gauss-Seidel? And so I'll consider first the ordering problem. So if we imagine we're doing block Gauss-Seidel, where you've got an n-block system, you can simultaneously permute the rows and columns and evaluate the order differently, and that will get you a preconditioner that has a different convergence rate. And so, in fact, there's n factorial such permutations, and if you sort of naively loop through all of them trying to find the best, that would be n factorial complexity. And this problem actually is isomorphic to this problem known as the linear ordering problem, which is provably NP hard, but thankfully has 30 or 40 years of research behind it. And so we can pull a branch and bound solver with Lagrangian relaxation approach from this cited paper here and just use that in order to solve this sort of combinatoric optimization problem that we need to solve. Once we have that in place, then we need to consider, how do I need to couple physics for which I cannot essentially do away with that coupling using block Gauss-Seidel. So in this example here, you imagine that the physics represented by A and E are strongly coupled, such that if you do not basically monolithically treat the A, B, D, E system sort of wholesale together, you won't actually reach convergence. So on some of these systems, they're so tightly coupled that you essentially are forced to do that. So this again becomes like another combinatoric optimization problem where we want to essentially find the minimum number of block merges such that we reach some user-specified tolerance. And for that, we use a sort of greedy heuristic algorithm that we bootstrap using our linear ordering problem solver. So we essentially loop through, we find the correct ordering, we chase down the largest block in our preconditioner that gets ignored, we merge those blocks together, do the reordering, and keep repeating until we satisfy the condition in line 3. I'll note that we're also working to improve on this greedy approach by developing our own branch and bound approach that's bootstrapped using this linear ordering problem solver, but that's for future work. So now that I've shown you some ways that we can solve both our ordering problem and our grouping problem, we now actually have to figure out how to invert the various subblocks. And so if we revisit our user application, let's sort of dive into this function that I have shown on line 13 here. So in general, this result that I have shown here is that you sort of have to be able to accurately solve the subblocks to within some amount in order to get a good preconditioner. So, for example, if you get the preconditioner for D right, but you completely mess up A, it will essentially derail the progress of the entire solver. So you have to get all of the subblock solves right in order for this to be a good preconditioner. Well, rather than try to do anything smart, we essentially do the dumbest thing possible, which is to use an adaptive approach where we start with relatively simple and cheap solvers. We try them out, we see if they converge. If they don't converge well, we reject them, and then we move on to the next most robust solver. So in this example here, we'll try GMRes Jacobi first. If that doesn't work, I'll reject it and try various flavors of domain decomposition until I finally get to the point where I'm so desperate that I just throw a sparse direct solver at it. Now note that a user can provide custom settings for all of this. And in the future, we're also going to explore using block AMG approaches for the merged blocks. But the point is these parameters that I've shown here are actually reasonably good for a large class of problems. And so I'll actually show you some real performance numbers that we have from Sierra. So this first use case is for an ablation performance test. It's on one node of Amber, which is a machine at Sandia. We used to use this DDIOU1 solver, and for the duration of the test, it would take about 120 seconds in the linear solve phase. Now, if I sort of handcraft a Teko solver, I can bring that down by a factor of 2 to about 61 seconds. But then if I try out this preset, it actually beats what I could do by like another factor of 2. Which yields an overall 3.7x speed up in the linear solve time compared to DDIOU. Okay, well maybe I cheated and sort of tuned everything for this use case, so let's look at another example, which is this coupled chemistry performance case that was previously using domain decomposition with IOU as the preconditioner, but if you just swap to this Teko preset solver, you instantly get a 2.3x speed up in the solve time. Okay, let's go back to the thermal battery use case that I showed at the beginning. Before I started working on this project, they were actually just using sparse direct solvers because they did not have a solver that would work reliably on this case. And so if you try that and do it for the entire battery calculation, you spend almost 2 hours just doing linear solves. If you sort of carefully go through and hand choose the Teko setup, you can reduce that quite a bit to about 957 seconds. But again, the Teko preset actually beats what I'm able to sort of hand curate, leading to a 8.6x speed up end to end. 8.6x speed up in the linear solve time, which translates to like almost a factor of 2 speed up in the total end-to-end calculation. Okay, well, these three cases, clearly I sort of had control over them. Maybe I just really fixated on the solver settings and got them all to work. So here's a sort of in the wild case that we got from a user. It represents some porous flow case, and it's again, ran on Amber. And I'm going to compare the performance of using domain decomposition with IOU and our Teko preset. And again, we see like the linear solve time using our sort of black box domain decomposition approach takes almost 2,000 seconds, whereas using the preset shaves off almost a factor of 10, so 8.5x speed up in the linear solve phase. Like this one here? Yeah. Yep. Yeah, so my understanding is Mesos 2KLU2, what it will do is it will gather all of the degrees of freedom on a single node, compute the factorization, and then I think it applies the L and U factors in parallel. But it's serial on one node. Yeah, It's it's not going to scale well. Yeah. Yeah. Whereas the Teko one is in parallel. Yeah. Yeah, absolutely. But so obviously I could have improved it if I had tried out some sort of direct solver that could sort of better exploit the parallelism that was available. But it's sort of a losing approach to sort of optimize a solver that is not going to be.
There's a reason why we had an approach and moved it to one node.
Yeah.
That our distributed direct solvers don't scale.
Yeah, distributed direct solvers, like that's not an easy thing to do in a very scalable way. And I'll note again, like, this is what they were using before we started really investigating these features. Like, using a domain decomposition approach just did not work reliably on this use case. So I'll conclude by just saying that our physics-aware based preconditioners in Teko, they can certainly outperform these black box DDILU type preconditioners. But they certainly require a lot of expertise from the user. So sort of the point in all of these algorithms that I've shown is we can sort of automate a lot of that away and sort of provide the user with reasonable default settings. But they currently do require a little bit of a modification to the user code. And so in the future, we'll sort of try and wrap this such that we can drive everything through the Tefos parameter list. And then I'll finally conclude, like, these performance results are reasonable. Obviously, what I've shown with the adaptive subblock solver, we can probably do a lot better. But my point is that just by using this approach, I've actually been able to outperform my sort of hands-chosen solvers. Now, obviously, I may not be very good at choosing settings. But maybe that's the point. Like, if I can't do it, our users certainly can't. So it's good to sort of have this, it's good to sort of recover that sort of black box approach that you get, where you just feed in the matrix and out pops a preconditioner. And then I'll finally note, this is almost available in Trilinos develop. There's still a couple of issues that we need to resolve. And then similarly, I'm working on a preprint, but it's not yet ready. Thanks. Any questions? Jonathan?
So, do you have a sense in the examples you showed, like how far it had to go through the presets till the appropriate solver settings were identified?
So you mean like specifically the adaptive? No, I don't.
and once it was identified for these particular problems, was that just used from then on?
No, so this will actually monitor throughout the whole application. Every time a preconditioner is invoked, it will, say we're on number 2 here. We're trying out GMRes DDILU. We apply it, then we check this relative residual condition, and we do that for every preconditioner application.
Okay, but once you've identified, like, say, option number 2, then the next time you invoke it, you would use option number 2.
Yes, yeah. It remembers that it's stuck on option 2, and then there's also some machinery, say, like, oh, I've tried 100 solves, it's worked correctly, let me flush back to 1 in case I'm like stuck on some overly robust solver. So there's some mechanism to both remember, but to also eventually forget, yeah.